The International Network of Algerian Scientists, INAS, is a nonprofit organization founded in 2016 by Algerian academics and professionals residing in the USA. The motivation is to pay back the homeland and help elevate the level of education in Algeria. INAS's mission is to network Algerian competencies worldwide with counterparts in Algeria. Among its activities, INAS has organized a significant conference that took place outside of Washington, D.C., USA in 2019. The conferees identified several need areas in Algeria and agreed to work on 10 different projects covering areas ranging from education, healthcare, to agriculture and ecotourism, to name a few. The work is ongoing and progressing. INAS is adopting the most contemporary and proven scientific methods to address these issues. INAS's humble beginnings included a few members. Today, it accounts for hundreds of able Algerians from the world over. Their goal is to participate in the rebuilding process of our new Algeria. These able and proud Algerians combine diversity and expertise with benevolence to set a path for a bright future in Algeria. INAS uses a top technology platform to allow members to collaborate and exchange knowledge. As an organization, INAS has different departments that ensure professional support to all its members, projects, and events. We welcome all Algerian competencies worldwide to join us in our noble mission. Algeria is bigger than all of us. Let's stand up and be counted today.
All right, good afternoon, everyone, and thank you for joining us for another live with INAS on the project Earthquake Hazard Mitigation. This is Mohamed Amrouche. I'm the project leader, and today we would like to have another special lecture on the project Earthquake Hazard Mitigation. So this project aims to share the knowledge and academic know-how with the general public people through online webinars that we broadcast live. So for this year, today, we will have our first keynote speaker, who is going to take us outside of this world. So it's a very special course titled Martian Seismology as Seen by InSight Mission and the New Frontier of Planetary Seismology. So today we have the honor and the pleasure to welcome Dr. Taichi Kawamura, who kindly accepted to share with us the latest findings and the fundamentals of Martian seismology. Good afternoon, Professor Kawamura. Thank you very much for accepting our request.
Good afternoon, and thank you very much for the invitation.
Thank you. So I remind that Professor Dr. Taichi Kawamura is maître de conférence in the Institut de Physique du Globe de Paris, where he is one of the rarest and lunar and space seismologists working on lunar data and seismic and Martian seismic data. And today he's going to share with us the latest finding on the NASA InSight mission. So please, Taichi Kawamura, Sensei, the floor is yours. Go ahead.
Thank you very much. And hello, everyone. I'm Taichi Kawamura from Institut de Physique du Globe Paris. Or maybe I should say bonjour à tous, parce que Monsieur Armouche m'a dit que parce que c'est le webinaire algérien, peut-être ça va être sympa de dire quelques mots en français aussi. Donc, c'est grand plaisir pour moi pour faire cet séminaire. Et peut-être je me présente un petit peu pour vous donner un peu de contexte. Donc, je m'appelle Taichi Kawamura. Actuellement, je travaille à Paris, IPG. Donc, je commence mon étude à Tokyo, mais après, j'étais à Paris et je sais un peu faire aller-retour entre Japon et France. Et vous voyez ici des projets que je travaille avec. Donc, il y a des projets spéciaux du Japon. Vous voyez JAXA, c'est l'agent spécial du Japon. Donc, j'ai travaillé beaucoup sur Japon et aussi avec NASA. Et en fait, 90% de projets là, y compris l'observation sismologique. Donc, quand je me présente, je dis toujours je suis un sismologue extraterrestre. Donc, voilà. Donc, comme ça, je vous donne un peu de contexte en français. Après, je change en anglais parce que mon français n'est pas si bon. Donc, après, je vous donne qu'est-ce qu'on trouve avec la sismologie, notamment à l'autre planète. Et avec ça, je vais changer en anglais. So, thank you very much. It's my great pleasure, and I hope my French was not too bad. So today I will try to walk you through some interesting points on extraterrestrial seismology, but mainly I will talk about seismology on Mars. So first of all, when you hear planetary seismology or extraterrestrial seismology, maybe you might just say, hey, it's just a science fiction, but actually it's not. So here is a very new book. It's published a couple of years ago, titled Extraterrestrial Seismology, and I also participated on this book. So this is a book which discuss all the seismology outside the Earth. So this includes seismology on other planets such as Mars, on satellite, on the moon, and also on asteroids and comets. And finally, they also discuss some seismology on the sun. So as you see, it sounds like something very incredible, but it's really not the science fiction. It's real science that have been working on more than decades. And today, I will mainly talk about the seismology on Mars. But I would like to remind you that the first thing it's written in this book is this one. So planetary seismology, high risk, high return. So why high risk, high return? Because if you want to do seismology, you have to place seismometer on the planet's surface, which means that you have to land on it. So an orbiter cannot do this observation. So simply speaking, landing on other planet is much more difficult than orbiting other planet. So it's called high risk, but as well, it's high return. So it's difficult, but once you were able to realize this, you get many scientific output from this. And I will try to convince you that this is true, and we have been learning many things with seismology on Mars. So let's start about some episode of seismology and two planetary seismology. Of course, our episode 1 is on Earth. So I think you already know that on Earth, seismology is a very much established approach, and you see some observation on the crust, on the core, on the inner core, and now we have all the global seismic network that detects seismic events on daily basis. And you might also know that this kind of propagation of seismic waves tells us a lot about the internal structure of the planet. And one of the key things that we want to find out is exactly this structure inside Earth. So this part is not visible from outside. If you see Earth as a planet from outside, it looks like just a water planet. But if you cut inside, it's very rocky planet with mantle, core, including iron. So it looks very different from what you see from outside. And this is exactly what we want to do with seismology. So on Earth, now observation is carried out. It's very well established. And thus, we want to do it also outside the Earth. And our first approach was on the moon. So episode 2 is lunar seismology. And this was made possible by Apollo missions. During Apollo missions, we have 5 seismic stations from Apollo 11, 12, 14, 15, 16. But unfortunately, Apollo 11 only functioned for about 3 weeks. So when we say Apollo seismic network, we always talk about these 4 seismic stations, which is distributed in a triangular shape on the lunar near side. So this realized about 5.5 years of network observation, and we detected more than 13,000 events on the moon. And this is some example on the lunar events. And interestingly, we found that there was different types of quakes on the moon, such as impact, which is a meteorite impact that hits the ground and shakes the ground. And we also saw what we call a shallow moonquake, which is a very energetic event at depths about 100 to 200 kilometers. And we also found deep moonquake, which is observed at 900 kilometer depths and very relatively weak compared to shallow moonquakes. So what we found is that moon is seismically active, And with this, we were able to construct internal structure of the moon. And this was realized back in 1960s to 1970s. So we did ours, we did moon. Next step is on Mars. So seismology on Mars also started very old, which was during the Viking mission. But unfortunately, I would say Martian seismology was a succession of failure. So when we did the first seismic observation with Viking, we were not able to detect any seismic events. And why? This is because we were not able to put the seismometer on the ground. So you see the picture from Viking here, taken from the deck of the lander, and you see that seismometer is actually on the deck and was not placed on the ground. So what happened is that on Mars, there is strong wind blowing onto the lander. So this means that the wind shakes the lander and seismometer only detects these wind. So in the end, unfortunately, Martian seismometer became a wind sensor. And the second try was by Mars 96, which was a European mission, but this failed in the launch. So after the launch, it fell on the ocean. So this did not even reach Mars. So what happened is that the second seismometer, Martian seismometer, became an ocean bottom seismometer. So since then, we had no opportunity to carry out seismology on Mars, and here is InSight. So we proposed a new mission to Mars using seismometer in 2012, and at 2018, it was successfully launched. So this is actually the new start of Martian seismology, and this is what the NASA mission InSight does. Here you see the selfie of the InSight lander. So you see this is a picture taken by a camera on the robotic arm, and you see that here we have our seismometer. And I would say this InSight is really the first geophysical observation station that is deployed on Mars. So it has not only seismometer, but we also had heat flow probe, and we also have what we call APSS, which is the Auxiliary Payload Sensor Suite. So this is to help observe the environmental noise. So we have magnetometer, we have pressure sensor, wind sensor. So as I told you, in the context of Viking, wind is a very problematic thing on Martian seismology. They always create the noise. So it's very important that we also monitor the wind speed and the pressure variation with the seismic observation. And I also want to point out that this is very international mission. So seismometer is made by France, mainly made by France, with the collaboration with US, UK, Germany, and Swiss. And you see heat flow probe is made by Germany, and all the mission itself was organized by US. So this is a very international mission that was carried out. And so what does InSight want to do? As I told you, one of the main target of seismology is to study internal structure. So I listed some of the target of InSight here, such as crustal thickness, crustal stratification, mantle structure, core, heat flow, seismic activity. So these are the things we want to detect by InSight. And you see our knowledge before InSight, and basically speaking, we know almost nothing about this. So everything that we detect by InSight will put the new constraint on Mars and new finding on Mars. And this will give us a new point of view on activity on Mars. So let me a little bit go more further into InSight. So here's the InSight lander. This is the solar panel, and this is our seismometer. And you see here the robotic arm. So Viking was not able to detect any earthquakes because one of the reasons was it was on the deck. So it was up here and not here. So basically, we went all the way to Mars, but we missed the last meter for Viking. So to resolve this, we had this robotic arm that places the seismometer on the ground. And this is how it looks. I also want to remind you that this is pretty much well-protected sensor, because here, this is a raw sensor. This is a real main part of the sensor, which is covered by this is a thermal protection. So this gold thing is a thermal protection to avoid the noise from the thermal variation. And this white one is what we call windshield. So this is to protect the seismometer from windshield. So we already knew that on Mars, observation will be very complicated. We have many sources of noise. So we wanted to protect our seismometer as much as possible. And this is how it looks. Yes, and this is fully covered version of this. And when you place, it looks like this. So it's completely covered by windshield. So this is how it looks on the ground. And this is just one thing that I want to give you an idea. So this is observation made on the deck, which means that it's before we place the seismometer on the ground. And here you see the wind speed as a function of seismic signal recorded on the seismometer. So you see that this is very much well correlated, and you almost see one-to-one relation on this. And this is exactly the case for InSight, and all these kind of signal you see, this is coming from the wind. And this is partially because the ground is so soft that if you place on it, it will not stabilize, but every time you have the wind, it's kind of rattles. And you also see this, like here. It can even step on a small stone. And these all result in high noise condition on the deck. So I think this, and here we also see the same plot on given by Viking. So for Viking and for InSight, we see exactly the same thing if we are on the deck. It's the wind that always shakes the seismometer. So we need to place it on the ground. And this is, I hope you see the movie. So this is exactly the time when we place the seismometer, and you see that we see nothing here. But I will let you wait for a minute. So here, so this is the real landing of a seismometer on the ground. So I don't know if you see the sound, but if you see the sound, I think you heard the people clapping their hand and shouting out. So because we know that this will be critical for our observation, and I also want to point out that this was the first attempt made by NASA to place scientific instrument on the ground using robotic arm. So this was quite a challenge for InSight, and this made possible the seismic observation we are running on InSight. And this is how it looks right now. So we placed the seismometer here. Then we also had the deployment of the windshield, and this is how it looks. So once we placed the seismometer on the ground, what we found is Mars is very, very quiet in terms of seismic noise. And this is even quieter than on the Earth. So this is about the 1 day of data on InSight, and you see Z, east, north axis from our broadband seismometer called BBB. And when it's blue, it means it's quiet. And when it's red, it means that it's noisy. And you see the noise with the different frequency band from 0.101 Hertz to 1 Hertz. So you'll see that in many cases, you see everything in blue. And what you see on the bottom is the same plot, but made for pressure sensor. So you see that when the pressure sensor is active, in other words, when there is a many atmospheric activity, you see increase of noise on the seismometer. So you really see the relation between the atmospheric noise and the seismic noise. But you also see that in many cases it's completely blue, which means it's a very quiet condition. And just to give you some idea, what I did is I just superposed the Earth's typical noise model onto this. If you do this, you see everything that was blue before become red. So what this shows is that Mars is very, very quiet compared to the Earth in terms of seismic noise. And this makes it possible to detect Marsquake, which is not very, very strong. It's not like magnitude 9 or magnitude 7 we detect on the Earth. Let me give you some different points of view on this. So this is the noise level of the seismometer compared for different planet and satellite. So what you see is in color is this is a histogram of noise level observed on InSight. In other words, when it's yellow, it means that most of the time during the day, it's the noise level at this level. But if you see some broad range like this, it means that during the day, noise can change, which means that at low noise condition, the noise level is mainly here. But during the day, when it's noisy, the noise became very high over here. And I compare this to the noise of white, which is the Earth noise, and gray, which is the moon noise, lunar noise. So I think you really see that Mars is very quiet compared to Earth, and even with the compared with the moon, it's quiet. But this is because I think it's more than the sensitivity of the seismometer. Basically, moon is much more quieter than Mars, but it is very clear that Mars is very quiet compared to the Earth. Another thing I want to point out is these small lines you see here. So maybe you see this kind of vertical line here. So this is some burst of pressure signal, or what we call the dust devil. Dust devil is what you see over here. So it's a very small tornado that passes close by the seismometer. And when these things pass, it's also detected by seismometer and also with a pressure sensor. Because this is a low pressure that is moving. So this is very interesting observation made by InSight that when we have these kind of dust devils, we see these signal as a tilt on the ground. And I will go more deeply into this afterward. But now you see how the observation of the seismic observation on Mars looked like. And this is kind of like a summary of what we are seeing. So this is a day, so 1 day of data. And this first place is the first day we place the seismometer on the ground. And every day we add one line to this figure. And we are now at Sol 1000, which means that we are already observing seismic activity on Mars for 1000 days. So you see that yellow part is a very noisy time, and purple part is a quiet time. So you see that during the day, so about like noon, 13, it's very yellow, which means that it's very seismically noisy. But during the night, it's become very quiet. And this is the same plot made for the wind speed. And you see how similar they look. So we can say that during the day, we see mainly the wind noise. And during the night, wind stops and we see low noise condition. So with this kind of environment, we want to do seismology. And the first thing what we did was not really a seismology. We did not detect earthquake, but we detect pressure drops, which is or dust devils. This is what I told you a little bit before, but I would like to explain a little bit more. So this is a small tornado that is passing by, and this is seen as a low pressure on the pressure sensor. So you see the measurement from pressure sensor here, and you see all of a sudden the pressure drops, and this comes back. It means that this kind of small pressure drops or low pressure comes close to the station and goes away. And what is interesting is that since this is a low pressure, which means that the force is weaker compared to the other part, it kind of lifts up the ground, as you see on the figure. And this will create some tilt on the seismometer. And this tilt is observed by seismometer. I think if you want to imagine this, imagine as a very soft membrane, or you imagine some kind of like bed, and you have a vacuum cleaner that moving around. And when you have vacuum cleaner soaking up some place, you see some other place showing some tilt on the bed. So this is exactly what is happening for the pressure drop. And what is interesting about this is also visible from images, because this is a tornado that blow up the dust. We can see this as the line on the image. So you see here some black lines you see. This is exactly the dust devil track that the dust devil moved through and blew up all the dust. And that is why it looks like a line. And we were lucky enough that we were able to detect these with the image and the seismometer. So this is the image taken from a lander, and you see this small line which was created by dust devil, and this is exactly what we saw on the seismometer and the pressure sensor. So you really see that this observation is detected on seismometer and also on the pressure sensor. And here's a summary of many pressure drops that we detected. So you have 3-axis seismometer here, and you also see the pressure drops, pressure data. And what is interesting about this is this can tell us the subsurface structure of Mars. So you can imagine that if there's a tilt, but if the ground is perfectly rigid, we will see very small tilt. On the other hand, when the ground is soft, we see large displacement. So by using this, we were able to estimate the rigidity of the ground, and this is our first result. So here you have frequency with what we call the normal compliance, which is the measure of rigidity. And you see that this changes with frequency. Why does it change with frequency? Because basically, if you are low frequency, you are at longer wavelengths. So you see deeper into the ground, and vice versa. So what happens is that this frequency information can be converted to depths. And this is exactly what we did here. So now we changed this frequency compliance plot to depth Young's modulus plot. So you see that we see some very soft layer on top, which then we see some kind of constant rigidity afterward. And this is the result. This was actually the first result we reported in 2020. And we remade this analysis, and we saw very similar results. So what we found is there's a very soft layer on the top, which we think is a sand or regolith layer. Then we see a jump of rigidity. So what happens is that maybe you see small white thing here. So this is sand piled up on the ground. Then we go to much more rigid, coarse, rocky layer. So what we are seeing is this soft material as a very low rigidity region, then jumps to higher rigidity region. So by using this kind of atmospheric seismology, we call this atmospheric seismology, we were able to detect or investigate the first 100 meters of the Martian surface. But we want to go much more in deeper. And for this, seismic activity, atmospheric activity is not enough, and we have to detect earthquakes. But for this, we had to wait for a very long time. And after about 100 days on the Mars, we were able to detect the first earthquake, which you see over here. So this is again what we call a spectrogram. So this is the frequency on the y-axis, and the time on the x-axis. So this is a change in spectral content with time. And what you see is that there's a couple of different types of energy you see here. And I'd like to walk you through each one of this. So first thing you might see is this one, if you go in the chronological order. But this is atmospheric noise. And we know this because we have a pressure sensor on. So even when we see these kind of seas, we don't say that they are seismic waves. We say this is only the atmospheric noise. And I also want to draw your attention to this energy, which have very strange shape. And this is actually the arm movement. So what we found is that during this time, there was a robotic arm moving to do some operation. It may be taking a picture or moving something. And this is also detected on seismometer. And we know this from our observation plan or operation plan, so we can reject this. And the same thing for this one and this one. But this energy you see over here, we were not able to find any explanation for this. We cannot explain this by atmospheric pressure. We were not able to explain this by lander activity. So in the end, we concluded that this was the first Marsquake we detected on Mars, and this happened, it said so 128, so which means this is about 4 months after we landed and started the observation. And I want to tell you how excited I was to see this event. But this was not it. We continued to observe, and we also detected a new event which you see over here. And I would like to remind you that when you start to talk about seismology, we say P wave, S wave, and we do the location. And I'm sorry, I want to go back one figure. So this is the first Marsquake we identified, but I think you clearly see that the shape is not so very different from that of the Earth. We don't see any clear P wave or clear S wave, but it's kind of like you see these kind of scattered wave that gradually increases and gradually drops. So yes, we detect a Marsquake, but this was not optimal for seismic observation. But the second event we saw was really a seismic event that we were waiting for, because you see these two energy arrival, which we say is a P and a S, and we were able to locate this, and we found that this was coming from about 1,600 kilometers away from InSight. And you see, to just give you an image, you see how the seismic wave propagated to reach seismometer. So these two were one of the first quakes that we detected. But since then, we have been carrying out observation for about 1,000 days, and here's what you see. So this is again the evolution of noise during the mission, and now you have all the Marsquake that we detected on the figure. So you see now we have about I think at this point we have a little bit less than 1,000 events detected. Of course, not all of them is a very nice event, very clean event, but it's very interesting that we found that the Mars is still seismically active. And we compare this to the Earth or Moon, and not surprisingly, we found that seismic activity on Mars is somewhat between Moon and Earth. It's not as active as on the Earth, but it's more active compared to the Moon. Now that we have full catalog, which you have an access to, the catalog is already released and you can have a look, we are able to do these kind of studies. I also want to point out that we also keep track of noise level. So maybe you realize that we have this period where even during the night it's noisy. And this is another view, another way to have a look on this. So this is a day, and y-axis is a noise level, and you have all the seismic event detected. And you see this period where you have high noise level. So here we were simply saying we were not able to detect any Mars quakes, because compared to the noise level, all the detected seismic events you see here is below the noise level. But this kind of like very nicely illustrate that what we are seeing, the seismic activity we are seeing is not very strong. It's very weak. And thanks to this null void condition we have on Mars, we are able to detect these. And this is just to show you some recent activities. So this is Sol 1000. We have this huge event we observed, and it's kind of amazing that we found this exactly on the Sol 1000. We've had this one of the largest events we observed during the mission, and we also see these kind of small events. So this is 4 days, recent 4 days, what we are observing. So, and this is another view of this. So this is the distance, and this is the magnitude. So you see, we have these kind of clusters on the distance. Many of the event is focusing around, I would say 30 degrees. And we have some far events, such as the one you just saw on Sol 1000. And this kind of illustrates the distribution, the geological distribution or distance distribution of the Martian seismic activity that I will discuss more in detail later afterward. But I want to discuss a little bit on the types of Mars quake or types of quakes that we see. As you saw, we have the first event 128 and second event, which is 173, was pretty much different. And this is better illustrated here because I made some comparison, 1-to-1 comparison on this. So this is 173 event, which is we were able to detect P and S arrival clearly. And this is 128, which is pretty much scattered and difficult to pick P and S. And for comparison, I added earthquake and moonquake. And I think when you see this, you absolutely see that high frequency, this type of scattered earthquake is more similar to moonquake, and this where you can see P and S arrival, it looks more like earthquake. So what is interesting is we see two types of event on Mars, and we are calling this LF family, which stands for low frequency family, because the main energy is always at low frequency, about 0.1 to 1 hertz, and high frequency family, HF family, which the main energy is above 1 hertz or above 2.4 hertz. And you see that these two Marsquakes family resembles earthquake and moonquake respectively. And we are interpreting this as a difference in the propagation of these events. So what we are thinking about is these kind of low frequency event, LF type events, propagate mainly on the deeper part of Mars, which is likely a mantle or lower crust. So it doesn't see the scattering. On the other hand, this HF type event propagate shallow in the structure, so it is more scattered, and we see these kind of seismic signals. And this is exactly what we observe on the moon. So even by comparing these two different types of Marsquake, we were able to study some qualitative characteristic of Martian internal structure. Oh, sorry. I also want to point out the distribution of seismic source we observed. As I told you, many of the events focused on about 30 degrees distance. And this is not only the distance, but it's also the direction that is pretty much always similar. So if you plot all the seismic source location on the Martian map, most of them focus here, which is called Cerberus fossae. So this is actually the region that was predicted to be seismically active. And what we found is, yes, it is actually seismically active, and many of the events that we observe is coming from this region. So it is very interesting that we found this, and we are now investigating why this region is seismically active today, and maybe we can ask the question if there's any other place that can be seismically active as Cerberus fossae. So now you saw different types of Marsquake and different types of where they come from. Then I would like to finally conclude by walking you through the Martian internal structure that we obtained by InSight. Let's start from crust. So for the crust, what we did is we made the analysis called receiver function analysis. So this is a way to detect converted waves on the discontinuity. So when there is a discontinuity, the seismic wave propagated as P can convert it to S, and vice versa. So here, what we did is we tried to detect what we call this P to S converted waves, and here you see S to P converted wave. And you see there is some different peaks you see on this figure. And each peak represents these kind of converted phases. So with this, we were able to construct the shallow internal structure of Mars, which correspond to the crust. So this is what we see, but unfortunately, at this point, we were not able to distinguish between the two models, which is the 2-layered model and 3-layered model. So they both, so you see the observation here, and you see the synthetic receiver function that we made from 3-layer model and 2-layer model. And if you compare this synthetic result and the data, you pretty much see that both 2-layer model and 3-layer model is pretty much similar to the data. So at this point, we are not able to distinguish between the two, but this is already exciting that we were able to constrain the crustal thickness below InSight using this kind of receiver function analysis. And this kind of illustrates how the wave is converted, but I will not go pretty much in detail. So this is what we think we see below InSight. So there's two possibilities. One is thin crust model and one is a thick crust model. So if it's a thin crust model, we expect that the crustal thickness is about 20 kilometers with some discontinuity around at 9 to 10 kilometers. Another possibility, which the thicker crust, is the 39-kilometer crust with two discontinuity inside, about at 9 kilometers and 24 kilometers. So at this point, we are still continuing the investigation to distinguish between the two, but we now have a good idea that the Martian crust is about 20 to 40 kilometers. So we saw the crust. Let's go to mantle. So to investigate the mantle, we did not use the direct wave, but we discussed the reflected waves. So seismic wave, as you know, propagates inside Mars like this, and we not only see the direct wave, but we also see reflected waves. And I don't know if you see this. Yes, I hope you see this animation here. So the reflected phase we are using here is called SS, which means that this is a S wave that comes in and bounce back once at the surface and reaches. What is good about this is this propagates inside mantle twice. So it gives us more information on the mantle. And this is how we detected this. So for this, we used the autocorrelation technique. So we took the S wave as a reference and we calculate the autocorrelation to see if there's any reflected phase within the later energy. And this is the SS wave we detected from this seismic signal. So you see how small they are, but which is very, very clear when you do this kind of autocorrelation technique. So by using this, so this is a summary of all the event that was used to study mantle structure, and this is the first seismic velocity model on the mantle that we saw. And what is interesting is you see a slight decrease in the S velocity and maybe also for the P velocity. Of course, what this kind of low velocity or decrease in seismic velocity should be studied more from different point of view, such as thermodynamic evolution of Mars. But finding this is already interesting. And finally, let's go to the core. So to find the core, we also use the reflected phase, but this time this was a reflection from the core mantle boundary. So we took the very pretty much a similar approach as we did on mantle, and we calculate the autocorrelation of the event, and we were able to detect this SCS. But you see how small they are. You see it over here, and this is the true S, and you see how small they are. And if you see the autocorrelation, okay, there's of course you see a peak here, but there's also other peaks around. So how did we really confirm that this is a reflection for the core? First thing that we did was we compared this with the noise level. So we also had the atmospheric noise atmospheric observation, as you saw from the wind or pressure sensor. So with this, we were able to estimate the noise level expected from atmospheric noise, and this is the energy of these reflected phases. So this SCS, which is the core reflection, is just above the noise level, and we were able to say that this is not the noise, but this was really a seismic signal coming in. And another thing we did is we stacked SCS energy, reflected energy from different source locations. So we took many events that we were able to detect the candidate of SCS, and we stacked them to see if they stack up. And for this, we used the core radius. We did this by changing core radius. So when you define the core radius, we can have an expected time for SCS, and we can stack this. So if we have a good or correct core radius, the energy should stack up and enhance. On the other hand, if we have wrong core radius, the energy should cancel out or will not enhance and have a low energy level. But what we found is that at the core radius, about 1,830 kilometers, the energy stacks up, and we see a clear increase or clear improvement of signal to noise ratio, which confirms that this is actually the real core reflection phases. And this is pretty interesting because what we first thought was the core radius is about 1,400 or 2,000 kilometers, but what we found is pretty big core compared to what was predicted before. This means that the core has lower density because we cannot change the mass of Mars. When we have a larger core, which means that there is a smaller density for the core, which means we have more light materials inside the core. This information, how much light element we have on the core, is very interesting, especially we think about thermal evolution of Mars, and this is exactly what we are working on right now. So we saw crust, we saw mantle, we saw core, and here is the final result of InSight. So these were the things that we said we want to detect, and all the things written in green is what we were able to accomplish with InSight observation. So you have now the crust, we also see the stratification of the crust, mantle velocity, yes, we detected. Core, I did not explain much in detail, but we have a good constraint on the core that is wicked due to the reflection of energy. Core radius, we are able to obtain the density. We saw the seismic activity, and we also saw that there is a seismogenic region on Cerberus foci. So you'll see how successful we are after 1,000 days of observation, that InSight was able to uncover the mystery of Martian seismicity and Mars internal structure. One last few words on what is going wrong right now. To be honest, InSight is not in a very, very good state right now. Due to the dust coverage on the solar panel, we have some energy issue and we are starting to lack energy. So little by little, we are decreasing the observation, and we are expecting that we might have to stop the observation pretty soon. But let's see if there's a strong wind burst that can clean up the solar panel and give us more energy. But at this point, the status of InSight is not very optimal, but we do still continue the observation. Yes. So here's the conclusion. One message here is InSight is doing great. We were, after 1,000 days of observation, we were able to accomplish almost all the aim that we were wanted to do. And I want to point out that all the data from InSight is now public. You will be able to access to all the data after 3 months of delay compared to the science team. And all the data are here. So if you're interested, I really recommend you to have a look and try the first step of planetary seismology. With that said, I will conclude here, and thank you very much for your attention. Thank you.
Thank you very much, Dr. Kawamura, for your very insightful presentation. It's always a great pleasure to see all this new frontier science. This is something very new, and I was just checking through the references, and we see all publications are 2020 or 2021. This is just to show you how new this new science is. Also, thank you very much for covering the different aspects from the deployment of the InSight lander down to the how did you manage to map the different core and mantle of the inner Martian structure. So I would like to go to the Q&A session now. I remind you that if you have any questions, you can ask your questions on the comment sessions, and we will pick few questions, and Dr. Kawamura will be very happy to answer a few of them. So let me just go through the comment session and pick few questions from the audience here. First question is, thank you very much for the presentation. Wind seems to be a real problem for seismic observation on Mars. Why didn't we embed the seismometer inside the lander and prefer to go for an external arm deployment? Why didn't we place the seismogram inside the lander and make it landed instead of deploying an arm outside?
Okay, that is a very interesting question. So yes, actually what you see is, sorry, I think this is the best. So what you see here is the noise is very pragmatic, but at the same time, one key noise source is the lander itself. So lander will also shake, or inside the lander, there's many other things going on. For example, what we see is that if there's energy supplement inside the lander, this also generates magnetic noise on the seismic data. And if you are inside the lander, you start to see all the mode of the lander. So lander is not quiet. Lander is a main source of noise, I will say. So if you are inside the lander, you will avoid the wind noise, but will suffer from all the artifacts from the lander. Of course, this is completely a trade-off, which will be better. And this time we chose to deploy it on the ground. And I think this was a good choice because if you're on the lander, I think you see lots of other things. Maybe I can also show you this one. So here, I didn't discuss in detail, but this red one is the observation we made on the lander. So this is what we see on the lander. So first thing is that, okay, noise level is very high because this is inside the lander. It's always shaking by lander. So if you're inside the lander, we will see all of this. And I would like to draw your attention to all of this mode here. This is all the vibration mode of the lander itself. So this kind of illustrates very well how noisy lander can be. So we wanted to go away from lander as much as possible. So this is why we chose to place it on the ground, and I hope this answers your question.
Thank you very much. So yeah, I think the lander will definitely cause more noise than the Martian wind itself. Let's move to the next question from YouTube here. Does Mars have a plate tectonic or a stagnant lid regime like on Venus? Or if there is no tectonic on Mars, where these Marsquakes come from?
That is a very good question and interesting question. Okay, to be honest, okay, first of all, plate tectonics does not exist on Mars. It's completely a one rigid crust planet, so we don't expect any plate tectonics on Mars. So the question is, if there's no plate tectonics, what causes Marsquake? My answer is, I don't know. This is still an investigation. But why my first educated, not the guess, I think I should say something better than educated guess, is one hypothesis we have is that this is a global cooling of the planet. So when the planet formed, it is very hot. And after billions of years, it keeps on cooling down. And when it cools down, it continues to shrink. And this shrink will generate some stress inside Mars. And what we expect is this this shrink of the planet generates stress accumulation and generates Marsquakes. So we think that why we see these kind of Marsquake is these kind of global contraction is accumulating, and this, oops, what happened?
Okay, yeah. Sorry,
yes,
I'm sharing.
So,
yeah.
So what happens is that there's this kind of global contraction which accumulates some stress in the places such as Cerberus fossae and makes the break in the crust or rock that generates Marsquake. So this is our first hypothesis we have on the source of Marsquakes.
All right, thank you very much for your response, Dr. Kawamura. We will pick. We have so many other questions on the chat. Let's pick up from Sarah Kilal in LinkedIn. Thank you for the interesting presentation. Could you please state what are the similarities and differences between Earth seismology and Martian seismology? You've been working on a lot in Martian and lunar seismology, so I think this slide sums it pretty well. Maybe the long duration, from my experience, I know there is a long duration, but is there anything else you can highlight between seismology, lunar seismology, and Earth seismology in a nutshell?
Okay. If I were to start with some constraints on we have, so of course on Mars you have only one station. So we have to use one station to understand everything. This is already a huge challenge. And this is one observational constraint or observational aspect that we see a huge difference on Earth and the Moon. I mean, Earth and Mars. So even if we see this kind of Earth-like event, we have much more difficulty on detecting core phases or reflected phases, and this is already a challenge. And I think, okay, this figure is really a summary of my experience from working on Moon, Mars, and Earth. And I would say this kind of high frequency family is very rare, or maybe even not seen on Earth. So to be honest, many of the study right now is using LF family. All the discussion I had on the Crust Mantle core is using LF family. In other words, we are trying to use some classical seismology approach here. And this was pretty much successful for LF event. But actually, LF event is only, I would say, 10 to 20% of the seismic event we see. And many of them, or most of them, is HF family. So in other words, we are still missing 80% of science we can do on Mars seismology.
Okay.
And I would say this is the biggest difference and the biggest challenge we have. And I also want to comment that one of the scientists working on this HF family, I think she is one, not only, but one of the few seismologists who start to attack this HF family type that is not be able to understand with the classical approach. She is working with me, and she is a student from Algeria, so maybe that can be a interesting story for you.
Awesome. Very, very good. Thank you very much for your answer, Professor Kawamura. We will, sorry, we have so many questions. We'll just pick one last question because we are running out of time. We heard that the InSight is going through a hibernation period in the news due to some planetary level and sandstorms. Is this going to affect the mission lifespan?
Yes. Actually, this is exactly what you see over here. So, okay, dust storm can work in two ways. One is in a good way, where the storm comes and it brushes up all the sand on the solar panel, and it increases the energy. But the second thing is it blows up the dust in the air, so the sunlight will be weaker. So in this case, you are not able to generate energy, and unfortunately, we are in this situation. Yes, okay. I hope that, and this means that we might start to lose the lander soon.
Okay.
And this is exactly what I was discussing over here.
All right. I think, yeah, thank you very much, Dr. Kawamura, for your answers and so for your very high-level presentation again, especially for your time, because today is a weekend, so you kindly accepted to deliver this online lecture to the public. So I hope everybody enjoyed it. Again, thank you very much. We would like to thank you for being with us today in this first webinar for the Earthquake Hazard Mitigation Project in 2022. We will have our next guest speaker for the month of February again, so please stay tuned in our page on INAS. And on the behalf of all INAS members and all the audience, we would like to thank again Dr. Kawamura for his time and precious input. So thank you again, Dr. Kawamura, and hope to read you again in the near future.
Thank you very much. It was my great pleasure. And if you have any questions or if you're interested more, feel free to contact me.
Merci beaucoup, Dr. Kawamura. C'était un vrai plaisir de vous avoir et au plaisir de vous relire. Merci. And also, we would like to thank all the audience that were following this lecture online. Thank you very much.